So what about entropy changes of ideal gases? I mean, we've got two equations that relate differential entropy changes to other things that are a little more real, shall we say, things that we maybe have some intuition about: temperature, pressure, volume, and internal energy, as well as enthalpy. And of course, entropy is a real thing too. It's just more the nature of energy. Now, the interesting thing about it is, since it's a property of the matter, it's really the way that, or the amount, or the extent to which energy is spread out, then we can relate it to other properties, and that's really what these two equations do. Now, remember that differential changes in internal energy can be written as the constant volume heat capacity times the differential change in temperature. And also, of course, if we're talking about an ideal gas, then the pressure of that ideal gas can be written as RT over V, just rearranging the ideal gas law a little bit. And then we can make substitutions for the differential internal energy change and the pressure, and some nice simplifications occur. For example, in the first term, we've gotten rid of the internal energy, and we only have temperature and heat capacity. And in the second term, several things have canceled nicely. For example, temperature is gone. All we're left with is a constant R and volume, really, a differential change in volume as well as volume. So this is a nice change in the equation. Now, differential equations themselves are not particularly useful. They represent how things change in relationship to how other things change. But what we'd really like to do is integrate it. So if we integrate this equation from one state to the other, from state 1 to state 2, then integrating the left-hand side would give us the change in entropy between the two states, S2 less S1. And on the right-hand side, if we integrate the right-hand side, really we can break it up into two parts. We can integrate the first term and integrate the second. Notice the second is pretty easy to integrate. It's really a 1 over x dx form because the constant r just comes out of the integral. So we end up with natural logarithm of the volume ratio between the two states. The first term, though, we'll leave unintegrated. It's simply the integral CV over T, where CV itself, the constant volume heat capacity, is a function of temperature times the differential change in temperature. Now be careful here. You might look at that and say, well, can't you cancel those two temperatures? Well, the upper term in the numerator is not saying that, you know, it's constant volume heat capacity multiplied by temperature. Rather, it's simply saying the constant volume heat capacity, which we recognize, changes based on the particular temperature at which you evaluate the heat capacity. So it's really a functional form showing that the heat capacity depends on temperature. So we can't just integrate that from the get-go. We can play a similar game with the other tedious equation, as I like to call it, right? TDS equation. Where we represent the differential enthalpy change as Cp dt and represent the specific volume from the ideal gas law as RT over P. Making these substitutions, again, some things cancel nicely. For example, the first term ends up with Cp dt over T. The second term, notice that, of course, we've intentionally eliminated the volume, or the specific volume, but also the temperature goes away sort of for free. So we end up with a form kind of like what we had before, but now we've got pressure instead of volume, and we have a negative sign in the equation as well as the constant pressure heat capacity. We can integrate this differential equation as well, and here's where we end up. The math is very similar on the second term, and we will leave the first term unintegrated for the time being. Again, the heat capacity at constant pressure depends on the particular temperature of the ideal gas. So we ended up with two nice equations that will allow us to calculate entropy changes of ideal gases. However, I don't know about you, but I would prefer not to integrate if I don't have to. Now remember, the heat capacities really don't change a lot with temperature unless we're talking about a vast difference in temperature between state 1 and state 2. So really, most of the time we could take the heat capacities to be constant as long as the temperature change from state 1 to state 2, the limits across which we're integrating, as long as those two states are pretty close to each other in temperature, it should be okay. So a lot of times we will use average heat capacities and neglect the dependence of the heat capacity on temperature, pull it outside of the integral, and now we've got a 1 over TdT form, which again is just a natural logarithm type of of form. Be very careful here. It's pretty natural, obviously, that the specific volumes and therefore their ratio are absolute things, but the temperatures have to be in absolute units as well for the first term on the right-hand side of the equation. You can't put in degrees Celsius or degrees Fahrenheit and get anything out of this equation that means anything. You have to either use Rankine or Kelvin, depending on which system you're working in, obviously. And it turns out it doesn't actually matter which one of those you use. You'll get the same result. But anyway, this form of the equation is a little more convenient. Now, you'll notice in the back of the chapter, we're in chapter 6, look at the summary equations, and you'll notice that this equation appears. You might want to make a note of it and note that it is an equation for the entropy change of an ideal gas. So if I were to give you, say, air on a test and ask you to calculate the entropy change of that air as it goes from one temperature to another, this could be a go-to equation that might help you. Now, we could also use the second equation and calculate the entropy change of that same ideal gas, that air, from this equation. You might look at these two and say, well, which one's right? Well, the answer is both are correct. It really doesn't matter. Both will give you the same result. It's just one may be more convenient than the other, because while both depend on temperature, one depends on specific volume, the other one depends on pressure. So whichever one you've been given, just use the one that's easiest for you. It's kind of nice when you come across options. A lot of times it seems like there's only one equation that works, no, there's only one way to do things. Well, in this case, both equations are equally valid. But you have to be careful about these equations because there are restrictions on them. Number one, we have to be talking about an ideal gas. If you apply this to a liquid, you're wrong from the beginning, right? This doesn't work for liquids because we have invoked the ideal gas law. It's built into these equations, and the ideal gas law says nothing about liquids. In the same way, these equations only work when the difference between T1 and T2 is small. What does that mean? Well, that means when the heat capacity at T1 and the heat capacity at T2 are relatively close to each other. That may be a better way of saying it. Now, what is relatively close? Well, you have to make that decision yourself, but a lot of times, when the temperature changes by less than 1,000 degrees Celsius, less than 500 degrees Celsius, most of the time the heat capacity won't vary a whole lot. And so this is a good first pass, if you will, at estimating the entropy change for an ideal gas going between two states. So the restrictions on these equations is number one, ideal gas, and number two, constant heat capacity. Those are requirements before these equations are valid. Now, as I pointed out in the back of the chapter, these equations appear. You should probably highlight these restrictions. They are around the equations. It's just this author doesn't make it really clear. He says for ideal gases, semicolon or colon, and then writes a bunch of equations. And you may not look at that heading, that numbered heading. So be careful about this and make sure you know what restrictions go with what equation in the back of that chapter.